Section 4.5, Isosceles and Equilateral Triangles. Let's start out with diagramming the parts of an isosceles triangle. Here, we have an isosceles triangle which is defined as a triangle with two congruent sides. I have the sides identified with tick marks that shows that they are congruent. The congruent sides are labeled as legs. The other third side of the triangle is known as the base, so the base and each leg generate what we call base angles. So I have two congruent sides known as legs, and they help form with the base two base angles. The third point on the triangle is known as the vertex, and the vertex with the legs form the vertex angle. With an isosceles triangle, we can create what is called a line of symmetry. A line of symmetry from the vertex angle to the base. And this is going to be a perpendicular segment. And when that is formed, that means that is a line of symmetry, which means the left side of my isosceles triangle is the exact same distance away from the point on the right side of my isosceles triangle. In other words, it creates a perfect mirror image. So if this was on a piece of paper, I could fold on the line of symmetry and the left and right side would actually match up. On this slide, we have Theorem 4.3, which is the isosceles triangle theorem. It states, if two sides of a triangle are congruent, here I have segment AB congruent to segment AC in this triangle, there are the legs, then the angles opposite those sides are congruent. Therefore, the angles opposite my legs, which are the base angles, are congruent. Therefore, if segment AB is congruent to segment AC, then I know that angle B is congruent to angle C. Let's generate the proof for the isosceles triangle theorem. If I'm given segment AB is congruent to segment AC, and I also have that AD bisects angle BAC. If that's true, then I know that angle BAD is congruent to angle CAD. And that reason is for the definition of angle bisector. An angle bisector divides an angle into two congruent angles. The third step, I can state that AD is congruent to AD by reflexive property. Step 4, I now have the two interior triangles congruent. Therefore, I can state that BAD is congruent to triangle CAD. And that is because of side, angle, side. Step 5, I want to prove that angle B is congruent to angle C. And from the previous section, I know that I need to follow a proof, generate congruent triangles, then I can get parts of those triangles congruent by CP, CT, C. Therefore, angle B is congruent to angle C because of corresponding parts of congruent triangles are congruent. And this proves the isosceles triangle theorem. As in previous sections, if we've generated a theorem, a lot of times it's very important to also state the converse of that theorem. We have on our Theorem 4.3, if P then Q, the converse would be if Q then P. So now, using the isosceles triangle theorem, and now I can state the converse, which is if two angles of a triangle are congruent. So here, I have triangle ABC. I have angle B congruent to angle C. If this is true, then the sides opposite those angles are congruent. Therefore, the sides opposite, which would be AB, is congruent to side AC. Theorem 3.5 is extremely powerful in generating information inside of an isosceles triangle. Theorem 3.5 states the bisector of the vertex angle. Here we're given an isosceles triangle. My legs are A, B, and AC. The vertex angle would be BAC. The vertex is angle A. The base angles are B and C. AD is an angle bisector of the vertex angle. Therefore, that is the perpendicular bisector of the base. When I know that it generates perpendicular angles on the base. Therefore, ADC and ADB are both right angles, and that makes them both congruent. I also know that point D, being a perpendicular bisector, would be the midpoint of segment BC. Therefore, I can generate segment BD congruent to segment DC. And with this being an isosceles triangle, I also know that the sides AC and AB are congruent. They are the legs. And from the isosceles triangle theorem, I know that the base angles, or the angles opposite those congruent sides, are congruent. So with this theorem, I generate a lot of information inside of an isosceles triangle. A corollary is a statement that follows immediately from a theorem. It gives us an additional information about that theorem that we can take into other parts of geometry. The first corollary that we would like to look at is from theorem 4.3, the isosceles triangle theorem. It states if a triangle is equilateral. Recall that equilateral triangle is a triangle that has three congruent sides. I have one diagrammed here. The sides XY is congruent to side YZ is congruent to side XZ. If that is true, then that triangle also is equiangular. It makes sense because in an isosceles triangle, I'm given two congruent sides. That's two congruent angles. Also, recall we have a scalene triangle with no congruent sides. That would have no congruent angles. Now, to take that a step further, if I have three congruent sides, that tells me I have three congruent angles. That makes this triangle not only equilateral, but equiangular. Angle X is congruent to angle Y, is congruent to angle Z. The next corollary is from theorem 4.4. It's from the converse of the isosceles triangle theorem. Again, if I go back to a scalene triangle, no angles congruent, no sides congruent. An isosceles triangle, if two angles congruent, two sides are congruent. And here, if I have a triangle that is equiangular, that tells me that all the angles in the triangle are congruent. Then the triangle is equilateral. In other words, each segment in the triangle is congruent. Therefore, segment XY is congruent to segment XZ, which is congruent to segment ZY. On this slide, we have some examples. Here they want us to complete the following statements. We have a triangle with several embedded triangles that have arcs and tick marks. So let's start. Angle DEF is congruent to, well, here I have angle DEF. DEF is inside triangle DEF, which is given to be an isosceles triangle because I know the legs DE and DF. And I know from the isosceles triangle theorem, the angles opposite, or the base angles, are congruent. So if DEF is opposite one of the legs, then the congruent angle to it is the one opposite the other leg, which is DFE. Next, I have segment CB. Segment CB is the big triangle. I already know from the big triangle ACB that angle A is congruent to angle B. From the converse of the isosceles triangle theorem, it states that the sides opposite those angles are congruent. Therefore, I have segment BC congruent to segment AC. Angle CEF. CEF is in the top triangle of CEF, and I know that that is an isosceles triangle because of the double tick marks. And I know from the isosceles triangle theorem, the opposite angles are congruent. Therefore, the angle CEF is congruent to CFE. Next, they want us to name the vertex angle of triangle DEF. The vertex angle of triangle DEF is the angle formed by the two legs. Therefore, that would be angle EDF. Next, they want us to name the base angles of triangle CEF. The legs in triangle CEF are CE and CF. The base angles are opposite those legs, which are angle CEF and angle CFE. And our last question, they want us to name the legs in triangle ABC. In triangle ABC, I have the base angles denoted by the arcs. They are congruent. Therefore, the sides opposite them we know are congruent, but those are also the legs. And that would be segment AC and segment BC. Let's continue with some examples. Here, in each diagram, they want us to solve for the given values for x and y. In our first diagram, we're given two isosceles triangles, and we have to find the value of x and y. If we start on the top triangle, I don't know the value of either of the base angles. They are the opposite to congruent sides. Therefore, I can't find the third angle. But on the bottom triangle, I know that I'm given an isosceles triangle. Therefore, this angle is 67. Then I know that this angle has to be 67 degrees because base angles or angles opposite the congruent sides in an isosceles triangle are congruent. Now I can use the triangle sum theorem that three angles of a triangle must have a sum of 180 degrees. 67 plus 67 is going to give me 134. If I subtract that from 180 degrees, that will give me the value for x. Therefore, x is going to be 46 degrees. Now, x is 46 degrees. I know that this angle here also is 46 degrees because they are vertical angles, and vertical angles are congruent. In the top triangle, that's an isosceles triangle. Again, I know that the base angles are congruent. Therefore, these two angles must be 46 degrees. Now I can use the triangle sum theorem again to determine the value of y. These angles must add up to 180. 46 and 46 will be 92 degrees. And subtracting that from 180 is going to give me the value for y, which is 88 degrees. Therefore, x is 46 degrees and y is 88 degrees. Our next problem, I'm given another isosceles triangle. I know that because of the tick marks. Again, I know that the base angles are congruent. Therefore, I can find the value of each base angle. If I subtract 34 from 180, that's going to give me 146 degrees. 146 is the value of these two angles combined, but I know that they are congruent. Therefore, if I divide 146 by 2, that will give me the value of each one of those angles. So when I divide 146 by 2, that will give me 73 degrees for each of these angles. When I take a look at the diagram, I know that x and this angle form a linear pair. That means that they are supplementary. They add up to be 180 degrees. 73 from 180 leaves me the value of x to be 107. 107 degrees. The next diagram, I have an isosceles right triangle. I know that the three angles add up to 180 degrees. If this one is 90, these two angles must also add up to be 90. When I divide them by 2, that leaves the value of x to be 45 degrees. Our next diagram, we're given an isosceles triangle. I know that because of the tick marks. I know that I have a segment that is an angle bisector. And in this section, we learned that when I have a segment that's an angle bisector of the vertex angle, then that segment is the perpendicular bisector of the base. Since that's true, I know that this point is the midpoint of the base. So if from this point to this point is 12 feet, x also has to be 12 feet. Also, since it's a perpendicular bisector, the value of y has to be 90 degrees. The next diagram, I'm given an exterior angle. I know that I can find the value of this interior angle because these two are a linear pair. Their sum is 180 degrees. In other words, they are supplemental. So if I deduct 123 from 180 degrees, I'm going to get a value of 57 degrees for that interior angle. I'm given that these two segments are congruent. They are the legs of this isosceles triangle. The isosceles triangle theorem states if two sides of a triangle are congruent, then the angles opposite them are congruent. Therefore, the value of x has to be 57 degrees. These two angles inside the triangle add up to be 114 degrees. By the triangle sum theorem, I know that the value of these three angles must add up to be 180 degrees. Subtracting 114 from 180 degrees is going to give me the value for y, which I know is going to be 66 degrees. The next diagram, I'm given a quadrilateral, and this quadrilateral has two right angles. A lot of information we can generate from these two right angles is because this could be our transversal. These two lines are intersecting the transversal, and they are same side interior angles that are supplementary. I actually could state that these two segments are parallel by the theorem. If same side interior angles are supplementary, then the two lines cut by a transversal are parallel. If that's true, then I can determine the value of this angle because they are alternate interior angles, and this is 26 degrees. I also could have found the third angle of this triangle by the triangle sum theorem. Therefore, if I know that this is 90 degrees, these two acute angles must add up to 90 degrees. If I subtracted 26 from 90 degrees, that is going to give me 64. Then I could have just used this right angle, subtracted 90 and 64, and got the value of 26 again. Once I find this acute angle in this triangle, I know that this is an isosceles triangle. By the isosceles triangle theorem, I can simply state that if two sides of a triangle are congruent, the angles opposite them also are congruent. Therefore, x would be 26 degrees. To find y, I just use the triangle sum theorem. Three angles of a triangle must add up to 180. 26 and 26 is going to be 52. And deducting that from 180 degrees is going to give me 128 degrees for the value of y. Our next example has a triangle that has three segments congruent. Therefore, I know that this is an equilateral triangle. And from a corollary in this section, I know it is also an equiangular triangle. So all three angles in this triangle are congruent. They all have the value of x. And I can use the triangle sum theorem, add up these three angles, which would be x plus x plus x, which is 3x, and set it equal to 180 degrees. Divide by 3, and I get x equal to 60 degrees. So an equiangular triangle and an equilateral triangle has a value for its angles to be 60, 60, and 60. In my next example, I'm given a regular polygon. We know a polygon is a closed figure that has its segment intersecting the endpoints of other segments. Regular means that all segments in my polygon are congruent. This polygon has 8 sides. And from our previous Examples, we know if I have a scalene triangle, I have no angles or sides congruent. Isosceles triangle, I have 2 angles, 2 sides. Equilateral, I have 3 angles congruent and 3 congruent sides. Therefore, we're leading to believe that a regular polygon, like an equilateral triangle, has all sides and all angles congruent. If that is true, then I know each of these interior angles of my regular polygon must be congruent. If there are 8 sides, I know there are 8 congruent angles. What I can do is determine the angle sum of my polygon and divide by 8. The easiest procedure is to determine the exterior angle sum. On all regular polygons, the exterior angle sum is equal to 360 degrees. There are 8 exterior angles. Therefore, when I take 360 and divide by 8, I get 45 degrees. So this exterior angle to the polygon is 45 degrees. I know that they form a linear pair with the exterior and interior angle. Therefore, I know my interior angle must be supplementary. So therefore, this interior angle is 135 degrees. I know that I have an isosceles triangle. Therefore, my 2 base angles are congruent. So all I need to do is take 135 from 180 degrees. That gives me 45 degrees. And then divide 45 by 2 to achieve the value of each of these interior angles, which is the value of x. 45 divided by 2 gives me the value of x to be 22.5 degrees.